when we say quantifying population dynamics, we just mean putting some numbers to explain how a population is changing and will change into the future. And there's a few important concepts that we need to understand. First of all is crude birth rate. Crude birth rate is just the number of births per 1,000 individuals in a population, and that's over the space of a year. Let's look at an example country here. And let's consider some data involving them. Let's say that in the year 2010, this place had a population of 5 million people. And in 2010, there were 30,000 births. We can easily calculate the crude birth rate from that. Remember that we've got to get this out of 1,000. To do that, we just do births divided by population times by 1,000. And that gives us 30,000 divided by 5 million times by 1,000. And that gives us a value of 6 births per 1,000. So that's the crude birth rate for this nation. Crude death rate, this works roughly the same. Obviously, we're talking about deaths per 1,000 individuals of the population per year instead of births. But in order to do the maths behind it, it's roughly the same principle. So let's look at our example population again. Let's say in 2010, again, we're sticking with the same population. So it's 5 million people and there are 10,000 deaths in this year. So to calculate the crude death rate, we've just got to do deaths divided by population times by 1,000, which is 10,000 divided by 5 million times by 1,000. And if you put that into your calculator, you will get a crude death rate of 2 deaths per 1,000. Natural increase rate. Now, this is where we can use crude birth rate and crude death rate to give us some useful numbers as to how things are changing. So this is the rate of human growth expressed as a percentage change per year. Notice it's a percentage change. So let's go back to our data for this nation. We've already calculated our crude birth rate and crude death rate, which we've got here. Now, to get the natural increase rate, we've got to do the crude birth rate minus the crude death rate. We take that number and we divide it by 10 because we don't want to be using values per 1,000, which is what crude birth rate and crude death rate are, but we want to convert it into a percentage. So 1,000 divided by 10 gives us 100, so we're working with out of 100, which is a percentage. 6 minus 2 divided by 10 for this population gives us 0.4%. Now, what that means to us in the real world is that this population will increase in size by 0.4% per year, assuming that these conditions remain the same, assuming that the crude birth rate and crude death rate remain constant. Another important idea is something called doubling time, and this is just simply the time it takes in years for a population to double in size. Let's look at a really simple set of data, and let's say we've got a 1% increase per year, so that's a natural increase rate of 1%. We start off with a population of 1,000, and as they increase by 1% per year, this is what their population growth will look like. If we want to find the doubling time, all we've got to do is go up to a value of 2,000, because we started with 1,000, so we're going up to double that, which is 2,000. Read that off the graph here, and notice that the time it takes to do that is 70 years. Now, this is a really, really important number. It doesn't matter what size of population we begin with. If there is a 1% increase per year, the doubling time will always be 70 years for that population. Now, because that value is constant, that makes it really, really easy to calculate doubling time. Let's use our original population as an example here. Doubling time is equal to 70 divided by the natural increase rate. That's where that number 70 comes in really handy. So for our population, we've got 70 divided by 0.4. That's the natural increase rate we calculated for this population. 70 divided by 0.4 gives us a doubling time of 175 years. What that means is it'll take 175 years for this particular population to double in size, assuming that those values of crude birth rate and crude death rate remain the same. Another important value when considering population dynamics is the total fertility rate, and that is the average number of births a woman has over her lifetime. Now let's imagine we've got a total fertility rate of 2, and what that means is that the average woman in that population will give birth to 2 children in her lifetime. So this couple, if they have 2 children, that means that this woman has replaced herself in the population, and it also means that she has replaced her partner in the population. And so our population size would remain constant. So this number 2 can be considered as the replacement fertility. However, this is not strictly accurate. In actual fact, the numbers are a little bit different. In MEDCs, the replacement fertility value is around about 2.03. It's quite close to 2. In LEDCs, it's a little bit higher, 2.12. The reason for this is that not all children are going to grow up to be adults. We have to take infant mortality rates into consideration. The reason that values are different for less economically developed countries and more economically developed countries is that the standard of healthcare is lower in less economically developed countries, and therefore we would expect the infant mortality rate to be higher. It's really important to note that amongst all of these calculations, immigration and emigration have not been included. We've assumed that total birth rate, the crude birth rate and the crude death rate are the only things that are influencing the changes in population. And so it's really important to note that in reality, the population may differ through other factors, like people moving in and moving out of the nation.